In this lesson, we will talk about systems of linear equations in two variables. So a system of equations is simply two or more linear equations. And notice here that we have this bracket. So when you see that bracket, we know they're talking about a system, or obviously if they say it's a system of linear equations. So why is this different than what we've done so far? Why is it important? Well, quite often what we're going to do is we're going to look for being able to model a situation with two or more linear or sometimes nonlinear equations, and we're going to be looking for the solution to that system. So a solution to a system is an ordered pair that is a solution to both individual equations. So we're looking for that point where the two lines would cross. So for instance, here we have a situation where we have the total cost using the yellow cab versus the blue cab. So we can see if we're going 0, 1, 2, or 3 miles, well, up to 3 miles, that it would be cheaper for us, looking at the graph, to take the yellow cab company. After that point, so this point, these two things are equal. So what we learned in the interval of 0 to 3 is that yellow is cheaper. Now, in the interval 3 to infinity, so from here on, we can see that the blue cab is cheaper. The solution to this system would be the point 3, 8, which is right here, 3, 8. And so what do we know at that point? That both cabs cost, we're assuming that this is in dollars, cost $8, so that's the 8, when driving 3 miles. That's the 3. So the X represents the number of miles and the Y represents the cost. So at 3 miles, both cab companies cost $8. So we can see how this would be important to us is to not only find when things are equal to each other, but also find when one is more or less expensive than the other. We obviously have 3 choices when we have systems of 2 equations. So we have a system of 2 equations. It's possible that they would cross at just one point. Just like in our last example, 3, 8 was the solution. It's called one solution, and it's called consistent. Consistent because there's one or more solutions. So whenever you have a solution, it's a consistent system. It's independent because the equations represent different lines. So if they ask you about consistent, inconsistent, dependent, or independent, that's kind of what we're talking about. Now, it's possible that we have 2 lines that are parallel to each other, that will never ever cross, which means that we don't have a solution because the solution is, of course, when the 2 lines cross. This is called inconsistent because there are no solutions. Our last choice is that we have the same line twice. So this is, it looks like one line, but it's really 2 lines that are the same line stacked on top of each other. This has infinitely many solutions because think about all of the different parts where those 2 lines touch each other. It's everywhere on that line. This is also consistent because there is a solution, but it's dependent because the equations represent the same line. So the first thing we're going to do is just determine whether or not a point is a solution to the system. So starting with the point, I would take my first equation, I would replace my x with my x value and my y with my y value and see if that equation is true. So 16, does it equal -4 times -4? -4 times -4 is 16, and 16 does equal 16. Now, that doesn't mean it's a solution of the system. That means if I were to graph this line, it would go through the point -4, 16. In order for it to be a solution of the system, it also has to go through -4, 16 on this equation. So again, I'll take y and replace it with 16. I'll replace x with -4, and then I will do the math. So -4 times -2 is positive 8, and 8 plus 8 is 16, and 16 does equal 16, and therefore it is a solution. Since it's a solution to both of the equations, then we say yes, it's a solution to the system. So the point -4, 16 is a solution to the system. If you'd like, get onto Desmos and graph both of those equations, and you should be able to see that they would in fact cross at the point negative 416. Here's another example for us to try together. So I will again replace y with the y value. I will replace x with the x value, and then I will simplify each side. So I don't have to simplify anything on the left side. 3 times 2 is 6. 6 minus 2 is 4, and so 4 does equal 4. On the second one, replace y with 4, replace x with 2. We end up with 4 equals 4 plus 1, or 4 equals 5, which clearly is not true, and therefore no, it's not a solution of the system. That means this first line did go through the point 2, 4, but this line did not. Here are 2 questions for you to try, so press pause, try both questions, then press play to check your work. So we are checking the point 3, negative 1 to see if it's a solution to either system. So the first one, I'll replace y with negative 1. I will replace x with 3. I get 2 times 3, which is 6 minus 8. So negative 1 equals negative 2, which is not true, which means I don't even need to check my second equation, because if it doesn't go through my first equation, then it doesn't matter whether or not it goes through my second. So that would be a no. For the second, I'm replacing y with negative 1. I'm replacing x with 3. I end up with negative 6 plus 5, which is, of course, negative 1. So it checks out for the first equation. Because it does, I have to check it for the second equation. So I'm going to replace y with negative 1. I'm going to replace x with 3. I get negative 1 equals negative 1. And therefore, yes, it is a solution to this system of equations.